process designers have already simulated and sort of tested it out and come up with certain rules so that, and the only restraint that they put on a circuit designer is that they follow these rules when they're making the layout, so that when they actually go and do the process, all these problems will not occur. So it's very important when you make a layout that you need to understand the design rules that is specified by your foundry, and you need to follow those rules as much as possible. Now, usually the layout tools that you use will automatically have a design rule check. So you can draw, and it will also have an automatic drawing tool. So it will make sure that when you draw, you follow all the design rules, and then it will automatically check for your design rules. But because the co-enter software right now, we don't have access to the 45 nanometer PDK for the design rule check, you're going to sort of do this manually, okay? So, but you're going to use a very simple version of design rules, which is basically called as lambda rules. So, so the lambda rules is basically like, it tells you what dimensions you need to follow. For example, if you have two wires next to each other, it will tell you that the spacing between these wires has to be some 3 times a lambda. So all dimensions will be specified in terms of some lambda. So this would be some 6 lambda, this would be a single lambda, where your lambda is always defined as half of your minimum feature size, okay? Oops. Yeah. And your minimum feature size for 45 nanometer technology is 45 nanometers, okay? So if you decide to use this node, take half of this as your value of your lambda, okay? So I put that here, so take half of your minimum feature size in lambda. And this file basically contains all the designers. So you can just go through this. It specifies everything you need. For example, if you have a transistor here, you need to follow these, okay? So the reason why this thing is here is not because they want to make your life difficult, but there is a reason why this poly has to extend this way. It has to do with the way the process is designed. So please try to follow these rules as much as possible. For example, this spacing, it says R306, and R306 is here. So this spacing has to be about 4 lambda, okay? So that's all this is, so just follow this. So if you have a doubt about how much spacing I need to leave here or something, just refer to this material, figure out what the dimension has to be, and just follow this dimension.
Wait, R304, are they purposely extending the polysilicon to the left?
Yeah.
Why are they
if you decide to make this sort of a design, right?
Yeah.
Then you need to follow this rule.
No, it's just telling the poly to poly.
Yeah.
That's
okay, but you wouldn't do that.
Yeah.
Yeah.
You wouldn't do what?
Well, you wouldn't extend the
No,
bottom
you
one
don't
to the left.
necessarily have to do what they say they tell you to do. If you are making something like this, just follow the rule as well. Okay? Now, of course, not all these rules are applicable to you, but when you are confused about what spacing you need to leave on either side or something like that, just follow these rules. So there are a lot of rules. You can just, like, again, you don't have to worry too much about this. So when you design, so because you guys were complaining that drawing these rectangles are arbitrary, so this won't make it that arbitrary. So that's why we made these design rules. Then, okay.
why don't you just give the layout?
Then I would make my life difficult and your life easy.
It's only 6 transistors.
No, you should know how to make a layout.
I mean, it's a process, right?
Yeah.
Yeah, I mean, this course is about process. So
No, but
it doesn't involve
see, if we give you the layout, then everyone's layout would be the same, and you guys would probably figure out how all of your processes will almost be the same. So we want each one of your processes. So you can always place transistors in different ways, right? So we want to see how well you're able to pack the transistors and how much you're able to decrease the overall size of the entire test transistor, and then design your process accordingly.
And what about grading matrix? Is it decided?
I can't grade. Professor will grade, but don't worry too much about that, because I know he's a good grader. So. Believe me, he's a good grader. Okay, so has everyone heard of ITRS? So you know what ITRS is? Okay, it's called the International Technology Roadmap for Semiconductors. So it's basically a bunch of guys who join together and decide what they have to do next, okay? So every year they actually meet up and they come up with what sort of dimensions they want to achieve the next year and so on. So the good thing about ITRS is it has all the information you need for a given technology node, which you cannot find that easily elsewhere. So I would suggest reading this. Now, this has a lot of good information that you can go through. So it has information about how they went about to design a given technology node and information about basically the details of a technology node. But if you're like me and you don't want to read all this, then you can just go to this page and then, okay. Please use this high performance logic technology, okay? Because SRAM is based on high performance logic. All right. Okay. So this is long back, like 2003. But okay, so this is your 45 nanometer technology here. So it's the physical gate length is 45 nanometer. So these are reference values. You don't necessarily have to use these values, but you can understand that whatever you calculate has to be in this ballpark. So for 45 nanometer technology, your EOT, does everyone know what an EOT is? Okay, so EOT is basically the oxide thickness that you need if you're using SiO2. Okay, for this technology, for any technology, they need not necessarily use SiO2. They can use hafnium oxide, or they can use any other high K dielectric, but they'll always specify your equivalent oxide thickness if you use SiO2. So if you decide to use hafnium oxide, you need to multiply this by your dielectric, by the ratio of dielectric constant in hafnium oxide to SiO2 to get your actual physical thickness in hafnium oxide. Okay? So
is that 1.3?
This is 1.3 nanometer.
Is that for SiO2?
Yeah, it's SiO2. Okay. If you use hafnium oxide, just multiply by dielectric rate. So it will always be thicker and higher dielectric material.
Is our gate is going to be made of SiO2? Anything more?
Not necessarily. You have freedom there. I'm not sure. In 45 nanometer, do they use? Do you have any idea?
What is it?
Do they use hafnium oxide?
No, do they use SiO2?
Yeah, they use.
You don't have to worry too much about these parameters. Okay. So you do have to worry about this, okay? Parasitic source drain resistance. So it has to be within this limit. So this will help you to choose what length of the source drain regions you need and what doping you have to make it. And your threshold voltages that I've given earlier will help you decide the doping for your channel. So yeah.
There are so many rules. Which one we should follow?
No, that's why I said don't follow all of them.
Which one we should follow?
Think about what all you need for. Okay, I'll move on to the transistor part now because. I don't remember how it runs. Okay, so this is technically what you're going to design. Okay, so what are the things you need to design here? So first is the length of this N plus region that you have here. So you have to design this length, and then you will have to decide this length. You have to design what your doping here is, what your doping here is, and this is symmetric. So then you need to determine what your doping in the channel is. Okay? And this doping here is what will determine your threshold voltage. So you need to adjust this doping to get the required threshold voltage that you need. This, for our purpose, we are going to assume it's poly, okay? So we are not going into metal and high K. So this is going to be N plus polysilicon. This is your oxide, which you're going to assume to be SiO2, and say this has a particular oxide thickness Dox. And assume your body doping. So body doping is typically in the order of 10 power 15 to 10 power 16. So when you basically when you choose your silicon wafer in Coventer, just choose this doping, okay? So in the ballpark number between 10 power 15 10 power 16.
Sorry, what number is that?
10 power 15 to 10 power 16 per centimeter cube.
Is that just the background concentration?
Yeah, this is the substrate doping.
Okay.
So this is uniformly doped. So
Right.
uniformly doped substrate. The entire silicon wafer has this doping.
Right.
Yeah.
And so the channel doping is the opposite type of this background.
No. It's also okay. When you make NMOS, your substrate has to be P-type.
Right.
Even though your substrate is P-type, in order to get the required threshold voltage you need to make the doping a particular level, which you're going to calculate.
Okay.
So you need to make an implantation here and adjust your doping here so that you get that threshold voltage.
And that has to be P-type doping?
Yeah,
Okay.
because NMOS is P-type.
Right, yeah. Okay.
PMOS NMOS. N-type. Yeah. Of course, you need this height, okay? So don't bother about this height. This height is pretty complicated to design because you need to account for fringing fields and all, and we don't want to bother you with those fringing fields. So just choose this height some reasonable value, okay? Like don't make it 1 micron or something, but some reasonable value should be okay.
And what is that reasonable?
Don't ask me. That's what you have to find. Okay, parasitic source drain resistant. So you can just go over this. So in order to design this, you need RSD. You need to know what your parasitic source drain resistance is. In order to design this, you need to know what your threshold is. Okay. In order to design this again, you need to know both your threshold and you need to know what capacitance and gate control you need. So obviously you can figure out there are too many design parameters here and not enough equations to solve it. So that's the reason why I gave you this ITRS, okay? So you can, when you do a design, it's always an iterative process. Now you cannot figure out all the values at a single stage. So initially just assume some values from this page, calculate your threshold, and you can use those values to design your transistor, okay? There'll be a lot of unknowns here, so you have to assume some values, otherwise you can't solve these equations. Okay.
And then the P-well doping,
Huh?
the doping you gave us is actually the bulk silicon dope, right?
Yeah, that's the bulk
It's
silicon.
not the well, P-well.
No, it's not the well. It's the uniform doping throughout the
You
substrate.
have to find that out.
Yeah, so I'll tell you how to find it. Do you want me to go over this, or you guys already know how to find the threshold? No, I know you don't know, but I know inside. Okay. So two options. Either I can give you the formula, or I can explain how the band diagram works. So your choice.
Explain and give it.
Give it. No, I can only give you one thing. I give you the band diagram and you derive the formula. I give you the formula. Yeah.
Quick question. So to figure out the length of that doping, you need to know the parasitic source drain resistance.
Yes.
To figure out the smaller length there, you need to figure out the
Again, you have a lot of variables here. You don't have enough equations,
Okay.
so you need to assume certain things to design it.
Right, yeah, but I'm just going through what you said earlier. The smaller length for that
This one?
that shallow
Yeah.
shallow dope that low dope region.
Yeah.
I think you need to figure out your threshold voltage. Is that what you said?
No. This does not, actually it does determine to some extent in modern technology, but you don't have to bother. There are a lot of non-idealities here, but assuming this is a perfectly ideal transistor, only this determines the threshold.
the doping
of
channel.
the channel.
Okay.
Yes, and your oxide thickness. I'll give the formula and then you'll understand how it depends on.
So L1 is like
L1 is the length of this N
yeah.
plus.
Isn't that determined by the 4 lambda design rule?
No.
Yes.
No.
The 4 lambda is the space in.
No. Oh, you're saying this N plus region?
Yes.
Yeah.
No, it also depends on your source drain resistance. But as I'll tell you, you can assume this doping is so high that this resistance is negligible. So you can make it as long as you want.
Okay. So
But
L1
this
should
one
be
you
at,
have to, because this one is lightly doped, so it's highly resistive. So it
Yeah.
has to be within the source drain resistance. Yeah. Sorry.
Actually, you know what? Why do you dope that little area they're lightly at? Why don't
Okay.
you dope the entire thing heavily?
So the reason okay, so you all know how a PN junction works, right?
Yeah.
So when you have a PN junction, the built-in potential here, okay, is usually some logarithm function of the product of the dopings here and here. So it will be something like this, KT over Q. So it looks something like this.
Yeah.
Okay. So your built-in potential depends on your doping. If you make the doping here very heavy, then your built-in potential and your electric field here will be so high that the material can actually break down.
Oh, okay.
And also, when you have electrons sort of going towards the drain end, they get accelerated so high that they actually tunnel through this oxide and go to the gate. And that can actually accumulate charge here. And by accumulating charge here, you can actually change your threshold voltage.
Okay.
So there are a lot of non-idealities in this transistor. So that's generally why you would make this region lightly doped. And the reason, okay guys, you need to make this as shallow as possible, okay? Now, I would tell you to make it shallow because it's challenging to make it shallow from a process standpoint, so you need to know how to make it shallow. But from a device standpoint, by making it shallow, you can make the dependence of threshold voltage on your length of the transistor and on your applied voltage less. So by making this shallow, you actually make your threshold voltage more robust, okay? So you try to make this as shallow as possible, and you need to design this doping, as I'll tell you soon. So, I don't know how to tell the band diagram. Okay, let's go over it very quickly. So this is your poly, this is your oxide, and this is your silicon region here, okay? So everyone knows what a Fermi level is, right? Yeah, okay. Your Fermi level at equilibrium is always a constant, okay? Are you sure you want me to go over this? Because
Yeah,
The formula.
is
yeah,
that-
this formula is fine.
because there's a huge derivation for making this formula, so. Okay. I like formulas better. Okay, your threshold voltage is okay, that's it. Your 5e here. Okay, this is called the surface band bending, okay? So I think I should draw the band diagram.
Two 5B is just strong inversion, right?
Yeah, exactly. You've taken a device course?
Yeah.
Okay, this is called as a flat band voltage, okay? So, Okay, this might look complicated, but it's actually very simple if you draw the band diagram and actually derive it. But for the moment now, I'll just tell you what this formula actually means, okay? So it's actually a form of Kirchhoff's voltage law. So Vt is like the voltage you apply between the gate and your source. This voltage is a sum of different voltage drops. So the gate voltage is equal to, in order to understand this flat band voltage, I need to draw the band diagram and we need to understand the flat band condition when I don't apply a bias, but just forget this for the moment. The applied gate voltage is equal to the voltage drop in the semiconductor plus the voltage drop in the oxide. That's all it is, okay? It's just a KVL equation. So this 2 phi b is so this is called as a surface band bending. So again, this is another transistor equation, okay? So I can go over this if I have time in the end, but for now, just assume this is the equation to solve it. This is the Boltzmann constant, temperature, the charge of an electron, natural logarithm. This is the intrinsic carrier concentration of silicon at room temperature. Just assume room temperature. Even though your device gets heated up, just assume room temperature. Then this is your dopant concentration in the channel. This is the thing you need to actually solve for, okay? This flat band voltage, now this is not very, so this you need to sort of understand how to calculate, and I'll go over that if I have time. This will change depending on your doping here, okay? So and the flat band voltage generally depends on what material you choose your gate as. So if you choose a metal, your flat band voltage will again be different. But I'll go over this if I have time. And please remember, these equations are for the NMOS, and the equations change for PMOS, okay? So you can refer to some material to figure out what the PMOS equations are, okay? These are available online. You can search for these formulas. So how would you solve this? So again, there are too many variables. You don't know enough variables to solve it. You know what the threshold voltage is because I've already given that to you. So say it's about 0.3 volts. So your flat band voltage will be something like this. You can assume your dopant, so your poly, okay? You want your poly to have minimum resistance as much as possible. So you try to dope this as much as possible. And because this is polysilicon, it can usually absorb more dopants than crystalline silicon. So you can assume this to be in the order of some 10 power 19 to 10 power 20, okay? So assume some reasonable value here. Assume some reasonable value there, and then Ni, you know, for silicon at 300 Kelvin, it's about 1.45 into 10 power 10, something like that, per centimeter cube. Plug in all these values here. Now this is a complicated intrinsic, you use MATLAB or something to solve for the doping. So if you know all these values, you can solve for the doping. So
is that minus kT by 2?
yeah, it's negative. Because when you have an NMOS with this particular doping, you need to apply negative voltage to create the flat band condition. So that's why it's negative. Again, this is not arbitrary, okay? I repeat this now. For the PMOS, this will completely change, okay? So please make sure you use the right equation for the right case. And for the PMOS, you need to look for the donor doping, not the acceptor doping. So, questions? No questions? Okay.
What was the PB called again?
Phi B?
Yeah.
This is surface band bending.
Okay.
I think it's better. So you wrote down this formula, right?
No, I haven't been able to actually. Yeah.
Okay, I can write it again towards the end of the class, and you can copy it.
Oh, okay. Gotcha. I can also get it from other people.
Oh yeah, I didn't think about that. Sorry. Okay, I'll go over this very quickly. Okay. So in the polysilicon, you have a conduction band, valence band, and because this is heavily doped, your Fermi level is very close to the conduction band. So you'll have the Fermi level will be somewhere here. So, okay. The oxide is an insulator. It has a huge band gap. It has its own conduction valence band. And then your silicon has its own conduction and valence band. And it's p doped. Okay, so your Fermi level will lie somewhere here. Now you can think of Fermi level as something that determines where your electrons will actually go. So because the Fermi level here is actually higher than the Fermi level here, your electron, you can think, this is not how it actually behaves, okay, but you can think of it in a way, in this way. Because the Fermi level here is higher than here, your electrons will generally go here to the lower energy level. So you would have a buildup of electrons here, you would have a sort of decrease in electrons here. So if I now join all these together, as I've done here, the band diagram will end up looking like now, when I join these together, I'll have a single Fermi level, okay? That's important because I'm assuming an equilibrium case right now. I have not applied any voltage across the transistor, so my Fermi level has to be fixed throughout. By definition, the Fermi level has to be constant at equilibrium. So this was initially p doped. Now, because my electrons had gone here, this region will sort of have more electrons now. So this will sort of bend somewhat closer. So by this conduction band bending closer to the Fermi level simply means that there's more electrons here, because this gap is what determines the electron concentration. And because your band gap has to be fixed, your valence band will follow this conduction band and it will look something like this. Oops. Okay, this thing here is called as a band bending. And when you apply a voltage, this bending will sort of change because your Fermi level will sort of change depending on your applied voltage. And there will be some voltage drop in the oxide as well, so its band will sort of end up looking like this. And in the n-type material, it will sort of remain like this. Okay? There'll be some bending here, but you don't have to worry about that. Assume the poly is like so heavily doped that this bending is almost negligible. So this, I'm not applying any gate voltage. So the amount of voltage that I need to apply to make this flat, this whole thing flat, that is make this straight and make this straight, is called as a flat band voltage, okay? So that is what I gave the formula for. When you apply a gate bias, the Fermi levels will sort of shift depending on the bias I provide, and this thing will sort of bend even more and more. And ultimately, when this bending reaches a value 2 times phi b, is when your concentration at the surface, your electron concentration at the surface, becomes the same as your whole concentration in the p-type material. And that's when you say your device has reached threshold. Okay? So you need to consider all these things in order to calculate your threshold voltage and so on. But again, for this course, you don't have to understand all this. You can just use the formulas to calculate your doping. Any questions?
Can you explain the condition for the threshold voltage?
Yeah. So if I apply a voltage, right? Yeah. So this is my gate, and this is my body of the transistor. I apply a voltage here.
Yeah.
As I apply a voltage here, this band bending will sort of keep changing.
Yeah.
Okay. Once this bending reaches, so this thing is called as bending. So when this bends so much that this value here becomes 2 phi b, then your electron concentration at this region will become equal to your whole concentration in the bulk.
Your electron concentration where will become equal?
At the surface. At
Okay.
the surface. That is at the interface between the oxide and the silicon.
Okay. 2 phi b is a voltage. It's the value of a voltage.
Yeah,
Okay.
it's the volt equivalent of doping. Okay.
So you can draw that intrinsic energy.
No, I don't have time for all that. No, I mean, if we discuss this, we can go into device physics, and so it's a long story. So
Right. Yeah.
it's not a very fun story. So we'll forget that for a moment. So just use the equation. Okay. Okay. I'll go over this very quickly. Now, conductance is 1 over resistivity, rho L, A by L, right? Is this correct? I don't know. Okay. Yeah. So, what is conductivity for a semiconductor? Does everyone know, right? So, conductivity for a semiconductor is the electron concentration Q times mobility of the electron plus the hole concentration Q times mobility of the hole. Okay, this is by definition again. Okay. Now, you can assume here, you can assume in these n plus and n minus regions that your hole doping is almost negligible. So, just for simplicity, just ignore this. Okay, ignore this term. Just assume that it's so heavily n doped that this term is bigger than that term, and assume that this n here, so this electron doping, is approximately your donor doping. Okay, your Nd. So this formula just becomes Nd charge times the mobility of the electron. Okay, substitute that here. What do you get? You get Nd charge mobility of the electron times the area. So what is the area here? The area here is so it's this area. So if I was drawing the transistor, if I draw a rectangle here, it's the area of this rectangle. So going into this board. So what is that area? It's the width of the transistor times this, right? So assume this is a small differential length dx. Okay. Why? So you need to actually end up integrating this over this distance, and you end up integrating over the profile of your doping, because this is where you dope your material along the x direction. So this is just w dx over length. Okay. So your resistance is going to be 1 over. You have to integrate this. Okay.
Why is there an L over W term at the top?
I took the reciprocal.
Oh, okay.
Yeah. So this is the formula for the resistance of any region like this. Okay. Now, so in order to create this, you are actually implanting, right? So you have a concentration variation along this direction. This direction was the x direction. Okay. So say you have some Gaussian profile here. So all you're doing here is you're sort of integrating this profile, and the reciprocal of that profile times L over W is your resistance. Okay. Now, this resistance is the series of this region plus this region. Yeah, because this is n minus and this is n plus. So this has a resistance and this has a resistance as well. So it's actually this term plus another term for the resistance. So it's just a series of two resistors. So this term for this region, this term, another term similar to this, but with a different doping for this region. Now, like you said, you can assume this region is so heavily doped that the resistance is almost zero. Okay, so you can just figure out what your doping and profile for this region alone has to be by using a formula similar to this. Okay, now you need to make some assumptions here. Now, your mobility is in general going to depend on your doping, but assume that your doping is so uniform that this integral just becomes a product. Okay, you get what I'm saying, right? So it's engineering mathematics. So just take out this mobility. Just take the mobility at the peak doping. Times charge times the integral from 0 to xd nd dx. What is this?
Just D times XD.
It's the dose.
Oh yeah.
It's the implantation dose. So it's dose times charge times mobility at the peak doping, L over W. So you can figure out what your dose is. Okay? And try to make your implant as shallow as possible. The reason why is pretty hard to understand right now. It's based on charge sharing, and so you don't have to worry. But try to make your implant as shallow as possible. Okay? So let me say this, okay? The shallowest implant guy gets the highest grade. So again, I went through this very quickly, so if you guys have doubts, just ask. Okay, I think we ran out of time, but I'll just go over this again. Did everyone register for NanoHub? Has anyone used NanoHub before? Alright, so so just go to nanohub.org, register with your Facebook account. They don't post anything on Facebook, so you don't have to worry.
I think you can even register through like your UCLA account.
Oh, you can?
Yeah.
Oh, that's good, but just register. And so you have what's going on there? And you have set of tools, okay? So just choose this tool, MOS FET, okay? Now, again, this is not an additional software. This is basically to help you do those calculations. So if you are not that good at analytical calculations, you can always plug it in the simulation software and figure it out. So, now this system is very bad, okay? So it's running on Purdue's server, so it's incredibly slow. But just run it on the background, like if you don't have like. So it basically spoon feeds everything, okay? So you can just read this. There's a manual also. You can just look at it. It's like 3 pages manual. It's not a huge manual. You can read this, and you can basically specify everything. So for example, if I can choose my device type. So if I want an N-type device, I can choose N-type device. For doping, I suggest use Gaussian doping because usually your implants will have a Gaussian profile. So choose Gaussian source drain doping. And here you can set your channel length, you can set your source drain length, you can set your oxide thicknesses, your junction. So you just read through this, okay? So, and it also shows you here in a diagram form what each one of those dimensions actually refer to. So just set all the dimensions for your transistor. And if you go down, you can also set your doping. So you have the peak source drain doping. So it's usually very high because you want it degenerately doped. And then your channel doping, you need to calculate this, and you can check using this simulation that your threshold is right. Now, I suggest using the software because this is the only way you can prove that you're actually right. So when you do the presentation, you can show the simulation and say, yes, I was right. So that even though we cannot check your simulation and know whether you're right or wrong, you can at least justify.
I think.
Oh, just 5 minutes?
Yeah.
Is that okay? Okay, just 5 minutes. All right, thank you. Okay, model. Don't change anything here, okay? Everything is set default value, correct values. Set temperature is 300 Kelvin. For models, okay? So, okay, for models, choose drift diffusion model. Now I know 45 nanometer technology has some ballistic transport in it, but forget that for now. Just assume it's a drift diffusion model. And you can set how accurate your model should be. Now, sometimes when you set your model too accurate, your simulation does not converge. So try to make your model very simple, okay? So I am going to remove this because it takes some time to simulate it with that. And I think that's it. Oh yeah. Voltage sweep. So you can set what so this basically shows you your ID VG characteristics and ID VD characteristics. This specify your minimum voltage, your bias minimum voltage, number of points you want in your graph, and also plot your ID VD characteristics, your output characteristics, and just click simulate, and then you get the result. Okay. Now since this is running on Purdue's server, it's slow, but you can just wait for it. You can start packing. I'll post these formulas on the website, okay? So if you haven't taken this down, don't worry about it. I'll just.
You have a bunch of errors, by the way.
What?
You have a bunch of errors.
Oh, those are warnings. Just ignore the warnings. Because I don't know why those warnings come. I asked Purdue, they said they also don't know. So. Okay, so you got your IDVD. So this is your subthreshold characteristics of your transistor. So from here you can figure out that this threshold is approximately 0.5. So you can vary the doping and so on and see your transistor characteristics and sort of figure out what your threshold voltages are. And just one last thing, okay? So it shows you 3D plots of your doping. So you can see here how I've doped it. So this is your this is NMOS, right? So this is you have high N doping here and here, and this is a p-doped channel. So it's like I can also look at the contour plot to sort of see how the doping concentration. So you can see here. So this is the transistor structure. So you have N-dope regions and p-dope regions. You can also study how the doping varies as you bias the transistor. I think I'll just show that alone. This is your dopant concentrated final bias. So you can see how the electron concentration has increased. So that's because you created the inversion. Yep. So just play around with the software. Just ask me if you have questions. That's it.
What is the project do?